Hello and welcome everyone to our webinar AI/ML driven forecasting for power demand, supply and pricing. My name is Yukti and I will be your moderator today. One of my main jobs at SingleStore is to organize weekly AI webinars. We organize 2 webinars per week and we showcase AI use cases and different tools and technologies and their integration with SingleStore DB. I will start posting about our upcoming webinars every week. So if these topics are interesting to you, please feel free to connect with me on LinkedIn to stay in loop. I'd also love to hear for your feedback or any ideas or suggestions for any topics that you'd like to see in future sessions. We'd love to incorporate those, and we always like some ideas that are coming from the community. Okay, speaking of future sessions, we have got several amazing webinars coming up. On May 6th, we have uh, using AWS Bedrock and LangChain for private LLM app dev. On May 9th, we have live RAG comparison test, Pinecone versus Mongo versus Postgres versus SingleStore. And on May 15th, we have Zapier Central plus SingleStore plus full RAG agents. If any of these topics sound interesting to you, please RSVP right now. I hope to see you all there. And okay, coming back to today's topic, you're welcome to participate in the discussion throughout the session using the Zoom Q&A button. It's at the bottom of your console if you notice there. And we have an internal mission statement to answer all the questions that are thrown at us, even if that means following up with folks afterwards via email. And this has gotten a little difficult over time, but don't worry, ask away, even if there's a lot of questions or if it's a little overwhelming. No worries at all. No matter what the question is, we are ready to take it up. But make sure you have logged into your Zoom account with your name and email address because we won't be answering any anonymous questions. Also, we'd love for you guys to have a dynamic experience during this webinar. So please feel free to try out SingleStore notebooks. Anyone who tries it out today will be entered for a chance to win either new branded AirPods or Meta's new Ray-Ban LLM glasses. It's absolutely your choice. If you're lucky, we'll let you guys select. And I'll be putting a raffle link in the chat. It's also on your screen. You can scan the QR code. You guys can log in, and anyone who tries today will be, enrolled in the raffle. Also, you guys may know that SingleStore has had a free trial offer for many years. But in the past few weeks, we've also announced a new free share tier, which we'll talk about a bit later today. Okay, moving forward, please allow me to introduce our amazing speaker. We have the real star of the show, Ayush Pai. He is a computer science student at Georgia Tech, and we originally found him online after he created a viral AI basketball referee demo. Since then, we have partnered with him on many projects and many webinars. He's becoming a regular speaker at our webinars since really long. So thank you so much for joining, Ayush. We really appreciate you. And okay, so I think you can take over now. The floor is now yours.
Yeah. Thank you everyone for joining. Before we get into the show, just like a brief introduction into what SingleStore is, right? So who is SingleStore? It was really founded as MemSQL in 2011, and over the years, it's really grown into this huge platform where you can do so many different things. Here's kind of like the timeline over the last 10, 15 years, and it's really been growing to enormous heights. And now with the AI boom, it's becoming really, really popular as using a tool, as a popular tool for vector search, all these types of technologies that really go along with the AI. That's really coming up today. And you can see the growth that SingleStore has had in the last 15 years. And it's been really great to see all the new use cases that people have been using, all these new big companies using SingleStore to really enhance their technologies as we go forward. Just a little bit of how SingleStore works and what it kind of does. So I can say there's really 5 main features here. So we have fast ingest with CDC. So really have really good streaming data, transforms and bulk load data. It's not just about structured data. You can ingest directly into memory, and SingleStore is really good at that with unstructured and semi-constructed data for JSON, geospatial, time series. all these different types of data types it can be really good at. And, I think like this is kind of a quick visual to kind of support what I talked about. SingleStore is capable of supporting both analytics and transactional level workloads in the same system. And this is really made possible by SingleStore's patented storage engine kind of really built into the product, right? Regardless of the data source, we really use ultra fast ingest of data, variety of formats, and it's one single cloud product, right? So many different options. You can use Azure, GCP, AWS, and it really has this self-managed offering for any cloud service. And there's so many different use cases that we've been seeing for with all these webinars. Today specifically with AI forecast demanding. But yeah, I think we can get straight into the webinar. So thank you everyone for joining today and welcome. Again, I'm Ayush and I'm a computer science student at Georgia Tech. And today I'll be presenting the topic of AI ML driven forecasting for power demand and supply. And so this initial segment will kind of really set the groundwork for understanding the basic concepts of power demand and supply, which are really crucial for like the subsequent discussions on forecasting methodologies and really using AI ML to kind of really enhance this technology here. So power demand refers to the overall total amount of electricity and electrical energy consumed by the end users at any given moment, right? It kind of exhibits variability. So for instance, you can have certain hours a day where and certain hours a day, during the daytime, when the lights are on and stuff like that, you're using water. You're using anything, water heater, anything where it uses electricity during the day, stuff like that. It's using a lot of electricity. That kind of shows like the peaks in different moments. And you also have variability across different seasons. So winter, summer, you're going to have different electricity outputs. And yeah, so on the other hand, we have power supply. And this is kind of about generating and delivering electricity from, various sources to meet the demand. So it must be done dynamically, which is, to really, align with the consumption patterns because the biggest thing is, you really want this to be an efficient process. So you want to ensure stability and efficiency on the power grid. This really involves, ramping up the production or ramping down the production based on real-time demand, which can really vary throughout the day, right? And the intricacies of matching power and supply with the fluctuating demand really necessitates the sophisticated forecasting models, right? These models kind of really leverage machine learning, artificial intelligence to predict demand, supply needs, and also pricing with high accuracy, allowing for the optimized grid management and operational efficiency. Now more than ever, this is really, really important, right? As we have more and more technology coming on the grid, for example, you have electric cars, and electric cars are becoming more and more popular as we go. And in order to facilitate this, we're going to need a much more efficient and much more big overall, a power grid. And with all the, the chargers and all the superchargers out there, you're going to have this whole infrastructure in place. And the more efficient that we have our systems, the better. And that's why it's a really important discussion today, focusing on how these technologies will transform the energy sector and pave the way for, resilient and sustainable power systems. So, as we discussed, it is, really, the seamless interaction between power demand and supply is vital for grid stability, right? But it's also equally important to comprehend the economic mechanisms that really, allow us to govern the energy market. And this brings us to the realm of power pricing. So there are kind of three ways that we kind of see here. A lot of these companies do power pricing, and kind of what we'll kind of discuss today. We build a pricing model, and we'll get into that a little bit in our demo. But so wholesale. So first thing we're going to talk about is wholesale pricing, and this is at the core of energy market. This kind of really lies at the core of the energy market. This is where wholesale pricing happens, where it kind of represents the rate at which electricity is exchanged between the utility companies and the power generators before it even like touches the consumers, right? So this pricing is like kind of influenced by like a myriad of factors, including fuel costs, plant availability, government policies, market dynamics, etc. These can't really be controlled by the consumer, can't really be controlled by the power utilities. It's really just about, you know, the power generator companies. And as a result, these wholesale prices really exhibit significant fluctuations throughout the day and across seasons. So the next thing we'll talk about is retail pricing. So for the end customers, the retail pricing model comes into play. So this is really encompasses not only the cost of electricity generation, but also includes expenses related to transmission, distribution, other utility services, and understanding the retail pricing is really essential for consumers to gauge the energy usage and consumption habits to make informed decisions on their end of things. And a lot of the regions use this thing called dynamic pricing. And dynamic pricing is something that you'll need to use these AI ML techniques for, both from the end of the wholesale pricing and all the end from the retail pricing, right? So you have these dynamic pricing mechanisms implemented where electricity rates are very varied based on the time of day and the level of demand, right? So these fluctuating rates incentivize consumers to adjust their usage patterns, shifting consumption to off-peak hours when electricity is cheaper and more abundant, right? So dynamic pricing strategies play a crucial role in grid optimization, helping to balance the supply and demand, and ultimately reducing costs and helping the grid stability overall, right? You don't want everybody using electricity at the same time, um, because that can, or everyone using like if everyone's driving a self-driving car today, or not self-driving car, electric car today, that will put really big strains on the grid. I don't think the grid can facilitate it. So really about having these dynamic pricings allows us to have these incentivize these consumers to adjust their usage patterns. And overall, and then wait as we build the grid further and further, we can facilitate that. But really what's important now is kind of facilitating to what we have and making what we have the most efficient possible. So now that we've established the significance of power pricing dynamics and supply and demand within this industry, let's turn to our attention on the pivotal role of AI and ML in forecasting power demand, right? So AI and ML have really revolutionized the way that we predict future electricity demand, and by analyzing vast data sets and encompassing a vast majority of historical consumption patterns, weather conditions, economic indicators, population growth, temporal factors such as time of day and time of the year. These models can really provide really remarkable, accurate forecasts, right? And at the heart of these forecasting methods really lies the sophisticated algorithms such as time series analysis, regression techniques. These algorithms really dissect the historical data to identify patterns and trends, enabling them to really extrapolate future demand scenarios with a really high degree of precision, right? Additionally, we have these more advanced techniques such as, LSTMs, which stands for long short-term memory. It's a very popular type of neural network that allows you to do work with this sequential data that we're talking about, from the past. We're using historical data to predict what the demand will be in the future. It's a type of recurrent neural network that is increasingly being utilized, and LSTMs really excel in capturing these long-term dependencies in sequential data, make them really particularly well suited for these time series forecasting, and allows tasks like predicting power demand to be a lot easier, right? And the integration of AI and ML into power demand forecasting not only enhances the accuracy of prediction, but also really helps enable utilities to optimize resource allocation and mitigate risks with demand volatility. So AI and ML techniques really play a crucial role in predicting the output from diverse generation sources. With a particular emphasis on renewable energy sources such as wind and solar, these renewable sources are, inherently variable, because, with solar energy, for example, obviously during the sun, when the sun is out, you have a lot more electricity consumption, generation. versus, during nighttime, obviously. For wind, same situation there. It's very variable. And their output is heavily influenced by factors such as weather conditions, time of day. So by leveraging these advanced algorithms, AI and ML models can really anticipate the amount of power that will be used, be available from these sources at any given time. So that's very important. And also we talked about the general factors for, fossil fuels and all those other things. So one of the key challenges in integrating renewable energy into the grid is really the intermittency, right? So unlike other, traditional power plants, which can adjust their output according to demand, renewable sources like wind and solar are really subject to all these, weather conditions, which cause these natural fluctuations. AI and ML algorithms can historically analyze this data, historically analyze, weather patterns, wind patterns, stuff like that, and is able to forecast the expected output from these renewable sources, enabling utilities to better manage grid stability and optimize for resource allocation. And moreover, this AI and ML kind of driven forecasting kind of really empowers energy providers to have the most informed decisions regarding the optimal deployment of energy storage solutions, such as batteries, to store the excess renewable energy during the high periods of generation and, release it during the peak demand hours. So um, in the landscape of energy economics itself, the fluctuating nature of power prices really kind of shows that AI and ML can really emerge as pivotal tools here that can actually help you navigate this complexity of all these fluctuating demands, supplies, and how allows you to make a pricing model. So predictive models driven by AI ML meticulously, analyze historical price data alongside an array of influencing factors. You have, future price trends, and this allows you to create these future price trends, which these models decode, integrate, patterns and nonlinear relationships within these data sets. Things that you would not think about, things that you can see these obvious factors, but then there might be some other factors with valuable insights that allows you to optimize for your grid. So various models that we see here from traditional, autoregressive integrated moving average, which is a really common technique that's used. It stands for, ARIMA. It really is a common technique here that allows you to use, deep, these really powerful, tools and data and all this historical data to kind of, use this to create a really good power pricing dynamics. ARIMA and multivariate regression models provide really, really robust frameworks for modeling pricing dynamics based on historical data. Meanwhile, you have deep learning architectures such as recurrent neural networks, and LSTMs again that allow you to take these patterns and non-linear relationships and kind of model it in these power pricing dynamic situations. So, the impact of, accurate energy forecasting, this really allows you to have more enhanced resource management, allows you to, use these, allow these companies to optimize their generation capabilities, reduce waste, and this leads to more sustainable use of resources such as water, gas, and coal, all very important resources. And, this really allows us to reduce the carbon footprint by predicting peak demand times, adjusting supply accordingly. And companies can really minimize their reliance on less efficient carbon heavy backup sources and thereby reduce greenhouse gas emissions. And finally, cost efficiency, obviously improved forecasting allows you to better plan and allows the companies and really to lead to more significant cost savings in purchasing excess capacity and investing in unnecessary infrastructure. Okay, cool. Now that we got through that intro of this kind of world of forecasting demand for this energy grid, let's get into a code walkthrough and live demo here. Okay, so starting off with the code walkthrough, and I can pull up the demo as well. So essentially what we're building here is we're building a tool that allows us to take this historical data. And let me just open this in a better view. So this is some historical data that I'm not sure if it's real data. This is just some generated data I made based on some trends. And essentially these are some trends. So we have these dates here on the left. We have the temperature, we have the time of day, and we have the weekday, and we also have the demand. And the demand is in megawatts. So using these factors, how can we predict future trends? How can we predict future demand, create pricing models, stuff like that? Because this data is readily available to all these companies, to try to optimize for the future. And the question is really just how do we do it, right? So there's many different techniques I kind of discussed earlier today, but let's go through an initial demo to kind of show like what we're looking at here. So let me, 1 second, pull up the terminal. And by the way, everyone has access to run this as well. I think this will be shared in the chat if it hasn't already. And yeah, you can run this directly. All you have to do is download some dependencies and then run the power demand.py. But let's get into it. So let me just run it again. So power demand. Wait, 1 moment. Okay, so here we have, okay, so here we have, three kind of pages here. This first page that we see is our model that we created, right? I created a regression model that, takes in all this data and basically allows you to predict based on all that historical data. And essentially what it's doing here on this graph is you can see this is the predicted value versus the actual values. And the predicted value is, taking all this test parameters and then running it through this regression model that I created. And you can actually see it's pretty accurate. R-squared value of 0.83. Obviously, I don't have that many data points. More data points would make this a lot more better of a model. But we can also see here that we have, make a prediction using, these different parameters. So we have temperature, we have time of day, we have weekday, and we can see how those essentially kind of predict the demand based on this regression model. And finally, we also have a pricing model. So you can simulate pricing models based on power demand and see how that would affect your pricing model here and how much it would cost the utility providers to based on the price per megawatt and the high demand threshold we'll talk about in a little bit. And you can see, you can simulate based on pricing, how much it would cost for X amount of megawatts, stuff like that. And these aren't accurate numbers. These are just simulated numbers. I'm not really sure what the exact pricing is for something like this, but yeah, these are just simulated numbers based on this regression model here. But it kind of shows if you have the data, you can build something like this that's very useful. So let me just demonstrate this make prediction one first. So essentially you have, let's just say 20 degrees Celsius, time of day, just in the middle of the day, 12, and Tuesday. And you can click predict demand here. And what it's going to do is it's going to predict a power demand right here. So around 1600 megawatts. And it also has an AI analysis that takes in all these parameters, takes in the predicted power demand, and uses a large language model to actually generate AI analysis. So that's just an extra bit there that shows how you can integrate LLMs into this type of technology. But yeah, give me 1 moment here. Let me just bring this back here. So let's come back to the code and kind of explain how this is all working. And I'll go step by step through the different features that we have here to kind of show demonstrate like how this is working. So essentially the script begins with importing the necessary libraries and modules, obviously setting up the foundation for building a robust power demand and prediction. So each library here kind of has its own purpose. We have Streamlit, which allows us to see this cool UI. We have pandas. If you're not familiar, it's basically a a way of, making tables and, taking all this data from this unorganized CSV and then putting it into a format that you can put directly into a model. You have matplotlib, which creates these really good graphs here. And we have scikit-learn allows us to take these models like linear regression and take all the data and put it directly into there, and it would train the models for us. We have OpenAI for the large language model for the AI generated analysis. We have NumPy for some calculations, and yeah, scikit-learn and SingleStore, obviously. So SingleStore, what we're using it for, actually, I'll get into that a little bit later. Let's go like line by line through the code. So essentially the first step is to take the data and process it, right? And you might be wondering where we're getting the data from, and we're getting it from the CSV, which actually you can get it directly from the CSV, or you can get it from something more scalable, right? And if you want to make something scalable, you'd want to use something like SingleStore or something that's capable of taking a lot of data, taking in creating these tables, merging tables, doing whatever you want. In this example here, I only have 4 or 5 columns, but if you want to have something where if you have 50 columns, you want a bunch of different factors that affect your linear regression model, and take it all into consideration, right? These are just 4 factors, but I'm sure there's a lot more factors that go into this, and very, very specific factors as well that can really affect how the linear regression model turns out. You'd want to have something more scalable, such as SingleStore, to store your data. So right down here, we actually have where is it? Right here, we have our loading our data into a SingleStore table, into our database. So essentially what we do is we connect to SingleStore. S2 is SingleStore. So we do s2.connect, and then you would put in your database URL right here. And then inside of here, you would just do your normal SQL queries. So we're just creating, we're basically putting it into our table here, or actually, no, we're getting it from this table, which is called power demand data. And I can show you how you would actually put it in there with SingleStore. So we have this upload table.py, and essentially, you can create this table in SingleStore by essentially, if we have this CSV file locally, or if you have another source for your data, you can figure out how to configure it. Right now, we're just using the CSV file with all this data, and essentially what we're going to do is you're going to use this cur.execute, and cur is just basically the cursor from your connection. So you're running this SQL query that's saying create table with all these columns right here, and essentially, yeah, you would then take that from you'd actually take a you can put it directly in. It might be easier to just put it into a pandas table. Right here, I'm just taking putting in a pandas table from all this data right here, and then putting it directly into SingleStore. And what we can see in our SingleStore DB right here is we have all our data here, and a super scalable solution that allows you to get like a bunch of different columns, merge different tables, do whatever you want with the standard SQL queries, use vector capabilities if you have even more data with vectors, if you're trying to do something with formats that are not numerical, right? If you want to do, like, obviously we have like this one column here that's called day of the week, but maybe you want like some more more abstract categorical type data that's in pure English, right? And that's the type of data that you would want to use with SingleStore with, because you can use multiple types, you can use geospatial, you can use whatever you want in the situation. So yeah, that's how you upload that data to SingleStore, and then obviously we're getting the data right here. So once we get the data, we're putting it into a pandas data frame and returning the data frame. So that's where we're getting the data. So now we'll talk about a little bit about the data processor, right? So this class is really responsible for pre-processing the data set. It's a critical step in preparing the data for model training. So upon initialization of the data processing processor class, we receive the data set as an input that we kind of got from SingleStore, and it provides methods for encoding categorical features, preparing the data for training, splitting it into training sets, as we see here. And yeah, so basically that's all that's doing is taking the data that we get in. Also, we have an encoder because obviously we have this representation of weekday, which is in plain English. So we're going to want to encode it into, 0 through whatever, 0 through 6. And yeah, so that's the encoder for that. And then you would set up your X and Y variables here. And yeah, that's basically just setting up all the data. So also we have um, so we have this power demand model, right? And this is really for managing the power demand prediction model that we have. I'll show it in a little bit. So actually, I just demonstrated a little bit earlier, but we can play a little bit around with it. But upon initialization, it receives an instance of the data processor class, and essentially it gets all the preprocessed data, and then the class includes methods for training the data, training the model rather, evaluating the model, predicting them, predicting demand based on all these inputs that we see from this here. And yeah, so, or I guess on this page, yeah. So you have all these inputs right here, and that's what this method is doing, right? So you have temperature, time of day, weekday, and we're using the model that we created to predict, what is the power demand based on these three parameters. And obviously, as you build a bigger and bigger data set, you would want a lot more than three parameters, but this is just an example here. And yeah, so that's basically the code for creating this linear regression model, and then, evaluating it based on mean square error, and then, R2, and then, having a method to directly predict based on the user's parameters. We also have this code right here for getting a GPT analysis. So this is really important. A lot of different companies would like to integrate this now with all this, transformer technology coming out. You've seen GPT-4, you've seen Anthropic, their models, you've seen Google Gemini. And I was thinking about what's the best way to integrate this into something that can be used for, power demand and prediction. So here's just a prompt, just telling it what to do, basically generate a detailed analysis of predicted power, given the temperature, time of day and weekday, and then it tells it, the predicted demand of whatever the demand is, and then allows it to create a generator analysis. And this really is useful for, if you're talking to an end customer, or you're talking to someone who's not technical in the sense of, what these terms are. Obviously, these are three simple parameters, but if you have like a lot more difficult parameters to understand, and you're trying to, feed some of this directly to a consumer, on like have them understand their power demand output, how they can make it more efficient, stuff like that. You wouldn't want to feed them the raw parameters. And a lot of companies really want to focus on delivering the product well to the end customer. And this is something where this can be really useful, right? Taking all these like parameters in and taking the final output in and creating a detailed analysis in just plain English. And that's what we kind of see here. So I'll just go over this again. Let's do a different example. Let's say it's pretty hot outside, 50 degrees Celsius, very, very hot. We have, let's say around the same 9 a.m. And middle of the week, right? Predict the demand on this. Let's see what we get here. So a little bit more than earlier, 1700 megawatts. And we have this AI generated analysis, which can be directly sent to customers to understand better. And the hot temperature likely contributes to the increased cooling system. So it's kind of making analysis based on all these parameters, and then explaining kind of the reasons why we have these higher power demand. And we can try like maybe something outrageous like 100, just to see what this kind of does here. Kind of shows like the trend of the model, right? So as you have higher and higher temperature, you're going to have higher and higher megawatt output. That's just how the model is trained, based on these parameters. Like go like 10,000, just for example, we're gonna have like outrageously high numbers here. For more realistic, cold time of the year, 0 degrees. We have something where it's like midnight, and you have maybe Thursday, right? And we're gonna see what it's gonna predict here. So a lot lower, right? And that's just based on the historical trends, historical data that it trained this model on. And yeah, so that's kind of the code for that end of things for getting the GPT analysis. And just we already showed the loading data, and here's the code for the Streamlit pages. Not very important for this discussion, but just showing Here's where we're doing the make prediction. So we can see, we have these different options to select from, and based on, if they click the button, we generate the GPT analysis and we predict the demand. Yeah, so that's basically for that end of things. For the model evaluation, we already kind of saw the code for how this model is being generated, using all the data, the pre-processed data, to put that into a linear regression model. And then we take all our testing data and we kind of compare it based on the actual values and the predicted values that the linear regression model was able to generate here. And yeah, so on that end of things, we can go into the pricing model. So the pricing model simulation is pretty cool as well. So I can go to the code for that. So essentially what we're doing here is you can have different, you can have a base price, right? So this is the base price, and this is just completely at random numbers. I'm not really sure what the numbers are on this, but say we have a base price for megawatts of $30 per megawatt. And this is something where you can sell, these consumers can use, but mainly going to be used for utility companies trying to predict how much all this is going to cost for them, based on the demand and based on the base price, which is determined by these power plants, or solar companies or wind generation, stuff like that. That's the price that's generated there, and then so you can select that. You can make that variable. You also make this high demand threshold variable. So this kind of a threshold that allows you to a lot of these pricings are ranged on the demand. So you can say if it's anything above 1,500 megawatts, is going to be at a certain price, and anything above that certain high demand threshold, that you're gonna have like a lot higher of a price. And that can just be like a situation that you have directly with these power plants or stuff like that. So say let's say it's $75 for a high demand price. So here, this scroll bar allows you to basically, based on, total costs for megawatts, if you have, 500, um, you know, or no, around, 1,050 megawatts here, it'll cost you X amount of money. So 31,000 in this case. So you can play around with these and then create the best pricing model. And then, yeah, this will kind of simulate like the demand of megawatts versus the total cost here. So for example, if we have base price of $90 and high demand threshold of $1,900. We can change this up to this number needs to be higher, obviously, so maybe like $150. And that kind of simulates that. So this allows you to really simulate different pricing models based on power demand and adjust the base price and the high demand threshold to see how different scenarios affect the total cost of these, utility providers. And kind of how this code is working here. So, essentially what it's doing is the function enables users to kind of obviously simulate different pricing models based on power demand. So considers factors such as base price, high demand threshold. You also have, high demand price, simulated demand. This function facilitates, the exploration of various pricing strategies and their implications. So the script includes a load data, obviously. So um, we're loading the data directly into it that allows us to, take these demands. So what we're seeing here is the simulated demand values, and basically using that values to basically see if the simulated demand is greater than a certain threshold value, then you're going to be using, the high value, high demand price, stuff like that. These are just, simulated numbers here based on a hypothetical pricing model, whatever. You can price it based on, whatever situation you have. And you can play around with these numbers here and play around with these parameters. But this is just an example of how you can make this pricing model here. And yeah, that's pretty much it for this demo. I think we can have questions on it towards the end. Allow you guys to maybe, if you have any suggestions on what you want to try out, different things, scenarios you want to see. Obviously, you should have access to this after, or it's in the GitHub is probably in the chat, so you can access it directly and try playing around with it. If you have any different parameters you think of that would be really useful for predicting the power demand, and doing the model evaluation, that's definitely something you can incorporate. But getting back to the slides now, and just a couple more slides here before we can get questions. Some real world examples of using this technology and leveraging this technology to kind of to really allow us to, see how this technology is useful here. So first we have Google DeepMind and UK National Grid. So this was a big partnership. I think ended around 2019, but the objective was to, predict energy demand peaks and adjust the supply accordingly. And essentially what happened was Google DeepMind collaborated with, the UK National Grid to use machine learning algorithms that analyze historical data and real-time conditions to forecast electricity demand with really high precision. And the outcome of this was they aim to reduce energy wastage and improve the efficiency of electricity across the country. And it really helped balance the supply and demand more effectively. So we also have this example from Pacific Gas and Electric. So they also did a very similar thing to manage energy in real time. So they did predictive analytics. They did you know forecasting, a lot of these different techniques that we kind of saw on a smaller scale today, and use data from smart meters, weather stations to really anticipate where and when the demand will peak, and allowed Pacific Gas and Electric to manage the grid stability effectively, reducing the occurrence of blackouts, which is a really common caused by a lot of people using a lot of energy at once, and allows them to optimize energy from various sources, including renewables, which can be very fluctuating at a lot of times. And this other company I believe it's called Next Kraftwerk. It's one of Europe's largest virtual power plants, I believe in Germany. And they also use AI to integrate data from thousands of energy producing and energy consuming units to really predict power generation and demand. And it allowed them to effectively balance the grid by automatically adjusting production and consumption, which really, sorry, which really enhanced the profitability and renewability of these assets and yeah, maintained really grid stability. So all these companies are doing it. Maybe some local providers are doing it as well. And it's definitely going to be something in the future that really allows these companies to use more and more data to create better and better models to predict and make the grid more efficient. And the last slide here, so just the future of AI and energy forecasting. So obviously we have a lot of these advanced AI models coming out now, leveraging new AI architectures such as transformers, which have really shown significant success in understanding complex sequences. Obviously, we start off with the RNN, recurrent neural network, which allows you to take in data from the past and put it back into the network, and allows you to get multiple data. Then you had LSTMs come out, which were an improvement on RNNs. And obviously, the big boy now is transformers have really powered all these huge technology that we see today with GPT, Gemini, Claude, etc. And using transformers is really good for complex sequences and a lot of previous data, and it can be really greatly enhance prediction accuracy of renewable energy sources, demand spikes, and pricing fluctuations. You also have something that's really important to consider is precision and load forecasting. So it's really important to, as we go on, manage increased loads from electric vehicles, smart devices. A lot more things are relying on electricity nowadays, right? Not just basic electronics now, but obviously we have to support the entire electric car grid, and electric car infrastructure that's going on, and that's going to be a really important thing going forward. And finally, one thing to consider is optimization of storage and distribution. So AI really optimized energy storage and distribution by balancing renewable sources at peak demands by really maximizing renewable use and efficiency. And that's something that's going to be very important going forward. And these are kind of three things that I saw was really important as we go forward and kind of see the future of AI in this energy forecasting world. And with that, we can get into questions.
Yeah, Ayush, I think at the moment there's 6 open questions there. I think they very much focus around your presentation. I'm slightly at a loss to answer them. Sorry. This is kind of out of my field of expertise. But maybe you just want to sort of work through at least the
Yeah,
open questions. I think there's a couple of others that I've tried to answer, but I think, and I'll find them. Okay, so if we can just have a go at those. I think there's people specifically asking about the approach that you've taken and why you've used a model, and are you considering things like the time series element of it, for example, and so on. So
yeah,
it's general questions like that.
sure. I can just go through these from
Yeah.
yeah, so someone asked, how long does it take to train? I have found code where training takes, long several minutes. So for this example, this takes practically no time for a linear regression model. It's pretty much instant with the amount of data I have. But obviously, if you're using different architectures, using LSTMs, neural networks, they have to go through multiple epochs, multiple passes. So it's going to take longer depending on the model you're using. But yeah, in this scenario with my model here, it didn't take much time at all. Um, for the forecasting process, someone asked, let me just mark this as done. So for the forecasting process, is the model training on one step ahead, especially for ML models? So I think what this is asking is one step ahead forecasting. I'm not exactly sure what that's asking. Akmal, do you know a little bit more about that?
No, I mean, it sounds a bit like a kind of windowing,
Yeah,
but
seems like what they're asking.
mm,
So I'm not using, I believe I'm not using something like that for this specific model, but I think it can be used. There's definitely a lot of different techniques that are out there for this specific, type of instance. But I think, yeah, if you look more into it, I haven't looked specifically into that. It should be able to use that type of architecture in the future. And yeah, you can play around with this and see what you can make. So let's see. So the data that is used to be categorical. So the data that is to be used is data that is categorical, as in something that is physics based that would not work. Thing. Yeah. So yeah, categorical data kind of refers to data that cannot be like, quantum, I guess I don't know what the word for it is, but like with numbers, right? With numbers, something such as like temperature, you have time of day, stuff like that. That's a lot more quantitative. And if you have more abstract data types such as geospatial, physics simulations, you can have vectors, all of those things. It's very important to have something that can facilitate that. And a really common way of storing that is in vectors a lot of times, but also you can use there's geospatial types, there's a lot of different types you can use specifically with SingleStore. And a lot of those things can be really important for, power demand model. And that can go into this more than just these three basic parameters that we have here. Um, but yeah, I think, yeah, data that's categorical can be very important as well.
yeah, and I think that, I mean, generally for the database system, I mean, you can store pretty much anything in there. If you got stuff, I mean, the blob type will pretty much consume anything if you want. But I think specifically for modeling, it becomes a bit of a challenge. So things like one encoding, for example, if you're dealing with categorical data, that's a good approach, and I've used that myself in the past. That can help because sometimes representing things like, for example, whether someone's got a marital status, for example, or the number of children that they have. These values span more than just yes, no, or one and zero. So things like one encoding allow you to be able to specify these in a better way, if you like, in a numerical way that then an algorithm can consume better. Just some thoughts on that.
Yeah. And Nicole asks, is linear regression appropriate for time series data set? So it's probably not the best choice, but it was definitely the easiest thing to implement in such a demo. There's a lot better choices they could use that could be, more complex of an architecture. You can use, I kind of talked about earlier, ARIMA, which stands for autoregressive integrated moving average, which really allows for, a lot better processing of time series data. There's also something called, I believe, seasonal decomposition. You also have, a lot more, you have machine learning models that are a lot more tailored towards time series data, such as LSTMs, RNNs, stuff like that, that can really be useful for capturing the dynamics. But in this case, I was just trying to make something simple with, power output prediction based on, a couple of different factors. And in that scenario, it should work pretty well with just a linear regression. But obviously, yeah, scaling this upwards and making something more robust, obviously you would want to look into some of those more models that, yeah, definitely. Someone else, yeah, same. So Nicole also asked, what type of sampling design would you recommend for this price power forecasting problem? So sampling design, I believe, so I think the best way for this, I'm not really sure in what scenario you mean. I think if you're talking about sampling for the model, it would probably be, some sort of um, um, stratified random sample set or something like that. I'm not, but if you're talking in the sense of, building a data set, um, to be honest, I don't have too much experience on, building data sets for power demand, but I would say that, yeah, something where you can actually get the most, if you're not trying to use all the data, you want to get the most data that's equipped for making the model as robust as possible. And in that scenario, you would try to, yeah, you try to have a design that allows you to get that. Um, do you think the use of satellite images of weather condition as data can help support the forecasting process of energy? Definitely. That's something, obviously I couldn't incorporate into the small demo, but satellite images of weather can really help predict, for example, solar energy output. If there's a bunch of clouds, you're going to have less output from solar panels. If you have, wind conditions for, all these different things can go into the power supply and demand and can really help out there. And I'm sure like, these big companies probably already use that or in some way. But again, it's all about, taking that representation of an image and converting it into something that a model can be used, right? If you obviously you can't really feed the raw image in. So you'd have to do some type of, processing on that image, maybe run some CNN or something where you can extract the data directly from that image, figure out, if there's a bunch of clouds, if there's rainy clouds, stuff like that, whatever you're looking for in that image, extract that from directly from the image and then put it into a representation that can be used by some of these models. Obviously, the raw image will not be useful in that scenario. Um, let's see. So someone asked, who can be the end users of such an application, stakeholders on the generation side or the consumption side? So I think definitely both can be useful for this situation. So I think on my end, I kind of created something that is useful for, the utility providers themselves who, and this is something that I actually looked into a lot, which is sometimes the utility providers actually own the power plants. So they kind of, control both sides of things. They can control the side of, the supply, and they also control the demand. But sometimes a lot of the scenarios is where it's separated. Yeah, you have those utility companies who are responsible for distribution, and you also have power plant companies which are, completely separate. And in that scenario, I think both situations will be useful for this type of technology. Obviously, for power plants, it'd be really useful for them to understand, or not even power plants, but you also have solar energy corporations, you have wind energy, all these stuff. Based on a bunch of different scenarios. For power plants, it's basically, you have politics, you have, oil and gas, all these different things that go into the pricing of that and figuring out like what's the best way to supply and demand that. So I think that's a really important thing to consider on their end. And obviously on the utility end, it's, how much are they pricing? How much are consumers wanting? What's being used at certain times, time of day. If it's a really, cold season, it's a hot season, that's where they would want that type of data. So it's different data that they would use for these models, but I think either way, it'd be very useful for both sides of the spectrum. Yeah. Someone asked, where did you show the GPT analysis? So, and obviously you guys can run this directly once we're done here, but the GPT analysis is down here. So on the predict demand, you have GPT analysis that takes in all your parameters that you put in, and then gives you like a basic and like basic summary of what's happening here. And the reason why I kind of included this is really important to tailor to the end customer a lot of times. Obviously, giving raw data, obviously these are really simple raw data, but if you have very complex data, a lot of these companies use, it's not something that you can provide directly to the end user. Yeah, someone said interesting use case using SingleStore. I'm trying to read those. So what is SingleStore most significantly used for? Used for AI/ML solutions compared to other DBs. Akmal, do you want to answer this one?
Yes, Ayush, I can take that one. So the product, briefly, I know we're almost out of time, so let me just give you a quick history of the product. So originally started purely as in-memory OLTP processing. Used to be called MemSQL. You might come across it mentioned still on the, if you do a Google search or here or there, still on some websites. Subsequently added analytics capability through SingleStore, and now you've got a unified table type that handles both types. And it does a whole bunch of other stuff as well. So, for example, time series. Okay, I mean, we are not a purpose-built time series database. We do support some time series capability. We do geospatial support for JSON and vectors. Okay, so this is where the ML angle comes in, because you can actually do vector processing in the database engine itself, and that support has been there since 2017. I would say historically, probably some of the strong vertical markets that the product has come from, finance is always a good one. But we have across the board in many other domains where the product is used. It's actually on our website. Okay, I mean, there is a whole bunch of case studies, use cases, customer stories, but finance is definitely one area that is very strong for us. I mean, in fact, the support for vectors way back in 2017 actually came about as a request from one of our major financial customers. They wanted this, and that's where it was added. So hope that answers the question.
Sounds good. I think we can end it off and get into the giveaway winner.
Okay, all right. Thanks, Ayush and Akmal. You guys did a tremendous job. This was so interesting, Ayush. I personally learned so much because this actually has a very academic angle to it. So it's like really interesting. So for the people, those who joined late, there's a small reminder. We have several new sessions coming up over the next few days. On May 6th, we have using AWS Bedrock and LangChain for private LLM app dev. On May 9, we have live RAG comparison test, Pinecone versus Mongo versus Podress versus SingleStore. On May 15th, we have Zapier Central plus SingleStore full RAG agents. If any of these topics sound interesting to you, please RSVP right now. I hope to see you all there. And okay, the announcement that you guys have been waiting for. Today's raffle winner goes to John Drummond, who is a principal data scientist at Shell. Okay, congratulations, John. Congrats and thanks for joining. That's not you. Please don't give up. We are going to announce one more AirPods and Meta Ray-Bans winner by the end of the day. For anyone who has tried out today's demo by signing up at the raffle link, which was mentioned in the chat before, and you can scan the QR code on this slide and be eligible to win. I really want to thank Ayush for today's presentation and demo, and thanks everyone for joining. We really value your time and energy and the effort that you have put into attending this webinar. All right, thanks from SingleStore, and I hope you all have a great rest of the day and a nice weekend as well. Okay, I think we can wrap it up, right? Okay, bye.
Bye-bye.
Thank you, everyone.